Applied flow technology, and we're going to be talking about surge suppression fundamentals dealing with Waterhammer. And so in order to kick things off, how bad can Waterhammer really be? By the way, this is slide page 45, so it's about maybe a third of the way through your books. And so in order to kick things off, I'm going to start off with a couple of videos here.
Powering on. Welcome to Alltech Lansing.
Give me just a sec. Oh, it is? Okay. There we go. So the moral of the story is you want to avoid this so that you don't end up in a YouTube video on the internet. That's one example of Waterhammer pumping up against a valve that's not completely open yet. What's that?
Where was that?
Probably Southeast Asia, perhaps. I'm not sure. It was just a YouTube video that one of our people found. Then here's another one. How to get to the exciting parts. So who wants to stand next to that? That is another example of Waterhammer. So Waterhammer is caused by a number of different types of incidents that can happen. You might have thermodynamic Waterhammer, and that's where you'll have a sudden phase change, and that can send pressure velocity waves through a system at thousands of feet per second. You can have slug Waterhammer, where maybe you have a vapor pocket and then you have different slugs of fluid moving through a pipeline, and that can damage your system. And then we have what we call mechanical Waterhammer, which is due to mechanical events in a system. So if you have a pump trip or a pump start or a sudden valve closure, or if you have check valves that are slamming shut due to reverse fluid velocity, perhaps you have relief valves and control valves that are responding to system transients. All those different types of mechanical events can cause Waterhammer, which will send pressure and velocity waves throughout a piping system at thousands of feet per second. And you want to make sure that those surge pressures that you have don't exceed the various pressure ratings for the piping and sensitive equipment for your system. And you want to make sure that it's staying within codes and standards. And so there's a theoretical instantaneous Waterhammer equation that allows you to predict what the instantaneous pressure surge would be if you had a sudden valve closure. And so this introduces a parameter called the wave speed. That's essentially the acoustic velocity that will allow a pressure velocity wave to communicate itself through a system. And it's made up of several different parameters. The wave speed is based upon the liquid acoustic velocity, the liquid density and modulus of elasticity, pipe modulus of elasticity, wall thickness, and the Poisson ratio, and also how it is supported. And so if you were to run impulse and look in the help file, the wave speed equation is a big nasty looking thing here. Let's see. So this is the wave speed equation in all of its glory. That's all the parameters that make that up. That will dictate what the pressure surges will be. And this delta P equation right here is the instantaneous Waterhammer equation, also known as the Joukowsky equation, and it will allow you to predict what the theoretical additional pressure surge would be during a Waterhammer event. So let's assume that you have a sudden valve closure in a piping system, and let's say you're just delivering water through your pipe. Let's assume that it's a really low wave speed of 2,500 feet per second, and your fluid velocity is 10 feet per second inside the pipe, and your initial steady state pressure is 50 psi. When you slam that valve shut, you're assuming that the velocity is going from 10 feet per second to 0 in a very, very short period of time. And so this relationship allows you to predict what that pressure surge will be. So you've got your maximum pressure, which is based upon all these parameters that go into the equation here. There's your 10 feet per second, and it comes out to be adding 334 psi on top of your initial steady state pressure. So when you have just a very low wave speed here, which the wave speed is usually more on the order of 3,000 to 4,000 feet per second, and you have a relatively low velocity, that's going to result in a fairly high surge pressure. Usually this is conservative in determining what that momentary pressure surge will be at its maximum value, but sometimes it's not conservative. There are cases where if you have a sudden valve closure, and then when that fluid momentum changes direction, it can pull a vapor pocket and cause cavitation. And when that cavitation bubble collapses, it's like a balloon popping. And that bubble that pops inside the pipe can actually be higher than the maximum theoretical surge pressure. And so this is why you would use a more sophisticated method of doing your Waterhammer analysis in order to really get a feel for what the real maximum values would be if you had cavitation in your system. Cavitation can certainly play a significant role in your system if you have a valve that's slamming shut, or if you have a pump that trips. And cavitation introduces a significant amount of chaos into your piping system, and as you get more and more amounts of cavitation that's happening, if it's longer lived or really widespread throughout your system, it gets very hard to predict what the resulting pressure spikes will be because of the limitations of the mathematical models. One of the fundamental assumptions for AFT impulse is that the wave speed stays constant during the whole event. where in reality, if you have cavitation and vapor bubbles forming, the wave speed actually changes. And so that's something that reduces the reliability of the cavitation models if you get a lot of cavitation happening. Another is in reality, the vapor bubbles can move up and down the pipe, where impulse is going to predict them happening localized at their computation stations. And so the more cavitation that you have, the less reliable that the results are going to be. AFT Impulse has two different cavitation models that you can work with. There's the discrete vapor cavity model. It's been in Impulse for a long time, and it does really well for predicting very short-lived and localized amounts of cavitation. So if you have a vapor bubble that's less than around 10% of the computation station volume, and it collapses, it's that first or second vapor collapse that are going to be the most reliable pressure spikes that you'll see. We have another method called the discrete gas cavity model, and it will handle cavitation a little bit better, because with the discrete vapor cavity model, as you have more and more cavitation, it continues to add noise to the mathematical results. And so as you have vapor volumes that are constantly forming and collapsing and forming and collapsing, then that's going to potentially introduce mathematical anomalies of pressure spikes that may not be realistic. And so the discrete gas cavity model smooths that out a little bit more, which you'll see in a slide here in a second. And so the advantage with the discrete gas cavity model is it'll do a little bit better job for a few more of the initial vapor collapses when you have cavitation. And so this slide right here shows an example of a sudden valve closure. And so there's gravity flow through this really short system, and when that valve slams shut, you have an initial rise in pressure, and then as that pressure wave reflects off of this valve right here, the pressure wave is going to move back and it's going to communicate itself upstream. So it's like the traffic on I-25. You have people slamming on their brakes, then that's going to cause people behind to slam on their brakes as well. And so the amount of time it takes for the first person that stops to, a person a mile down the road, that's what we would call the communication time. And then eventually this person at the end knows that there's a stoppage up at the front. And so you're going to have pressure and velocity waves that are propagating back and forth between those two boundaries. So when the pressure wave decreases, it can potentially drop down to the vapor pressure, which is right at this location. And when the pressure drops to the vapor pressure, that's where you have a vapor cavity that will form. And once it collapses, it'll cause a fairly large pressure spike. Now, keep in mind that this is a fairly long pipe, and so this graph is only showing you what's happening at the valve. And so you want to make sure you pay attention to what's going on along the whole pipeline, and there's a way to do that in Impulse by the use of animations. So it allows you to look at a whole profile over time. And so you can see here that there are some fairly large pressure spikes. The red line is actual experimental data. The blue line is the discrete vapor cavity model, and the green line is the discrete gas cavity model. So as you can see, when that vapor bubble collapses, both of the cavitation models are matching their measured data pretty well. Even when it gets to these pressure spikes here, once you have pressure waves that are reflected back from the reservoir back onto the valve. At that point, you will have another drop in pressure down to the vapor pressure, and you have more vapor bubbles that are forming again. And then once they collapse, you're going to have another pressure spike. Now, as you can see, in comparison to the red line for the measured data, the discrete gas cavity model is following the measured data a lot better than the discrete gas cavity model. So that's why we talk about these assumptions where for both cavitation models, we're assuming that the vapor bubbles are staying localized at their computation stations and that they're small. So as long as your vapor bubbles are staying between 10 to 15% of the computation station volume, which in impulse it's going to take a pipe and it's going to break it up into chunks. That's how it's able to get the new pressure and flow rate at every time step during a transient. And so as long as your vapor volumes are small around this area here, then your results are going to be more realistic. But as your vapor volumes continue to grow, as you continue to have more and more cavitation, then the results can start to deviate from what's actually happening in reality. And so as you can see here, that way out into these additional vapor collapses, the discrete gas cavity model is still doing a really good job following measured data at that point.
Powering off.
Okay. With that, I'm going to power this back on to show a couple more videos here.
Powering on. Welcome to Alltech Lansing.
Yes, so what we call mechanical, we just mean that something mechanical is going on to cause that type of a transient. Yeah, if you had, so impulse doesn't model two-phase flow. So if you have a sudden, if you have a fluid that is suddenly flashing, then that can cause Waterhammer. I'm not sure if that will be as significant as it is in those graphs. You'd have to get a more sophisticated model that can do that, and so that's HYSYS might be able to do it, Olga, things that are much more sophisticated mathematical models that handle primarily two-phase flow a lot better. And so by mechanical we mean a pump trip or a valve that closes or a control valve that is responding to other transients that are happening in the system. A pump startup as well. And you know, that's a very good question, because a lot of people will say, well, we don't deal with Waterhammer in our system. Well, if you start a pump, you're going to have Waterhammer. The question is, how bad is it going to get? And so if you are able to do a model where you show a pump that's ramping up over time and all the resulting pressures are staying below your maximum allowables and whatnot, then you're okay. But if you have an accident where let's say somebody's walking down the pipeline and they slip or trip and they try to grab onto a valve because it's just natural instinct to grab something to keep yourself from falling, and it ends up slamming that valve shut. The pipes could potentially burst or collapse, all depending on what the situation is. And so that's what we mean by a mechanical Waterhammer. Does that answer your question? Let's see, Waterhammer IIHR. Let's see. I don't need that.
As was shown in the first film, the sudden closure of a valve at the end of a long pipe causes an elastic surge to be propagated back and forth between valve and reservoir.
So this is just another, this is basically an animation of what the pressure and velocity waves are doing when you have a sudden valve closure. And so when you have that sudden valve closure, you have an initial pressure spike. So this is a pressure wave, and it's going to move back towards the boundary where it's like a reservoir, and it's going to reflect off that boundary, and when it reflects, it will reflect in the negative direction.
At the end of a long pipe causes an elastic surge to be propagated.
Well, when it goes there and back, and then it comes back the second time.
At the reservoir end of the pipe, it is always reflected negatively. and at the valve end it is always reflected positively, as a result of which pressure fluctuates rapidly between positive and negative values. The waveform being influenced also by the elasticity and resistance of the pipe. If the initial velocity of the water is very high, the initial pressure rise can be so great as to cause rupture of the pipe. Conversely, the reduction in pressure when the wave becomes negative.
So that's cavitation, that vapor bubble right there.
Seen here in slow motion. The initial vapor pocket thereafter collapsing against the valve and then tending to reform repeatedly. Because of the noise that is produced by the sound wave in either case, the phenomenon is very aptly called Waterhammer.
And then next one, GFA.
GEFA Prozesstechnik. Your partner for valve technology. The Waterhammer effect. What is really happening during Waterhammer effect? The following pictures are taken with a high-speed camera with 1000 frames per second.
So that's cavitation right there.
Focus on that forces that are generated.
And then it comes back and it slams back into the valve again.
Waterhammer effect is activated by fast closing of a valve. Forces during Waterhammer effect. In proper speed, these effects are not visible to the naked eye. The pictures of the high-speed camera show how a steam vacuum is generated, how the water column is pulled back and punching on the valve. Consequences of Waterhammer effect. In slow motion you see how water spray squirts out of the flange gasket area. The studs are stretched and at the same time the whole construction is spoiled with a deflection of 15 millimeters. The forces. Vacuum is generated and pulls the water column back with a vacuum pressure of 0.1 to 0.2 bar. The measured distance for the backflow is 30 centimeters. Water covers this distance within 64 frames, that means in 64 milliseconds. "30 centimeters comply 4.7 meters per second or 17 kilometers per hour. This is comparable to the speed of a cyclist. Now steam bubbles are decomposed and deceleration begins. For comparison, a pursuit plane reaches 10 G at most. In an accident, deceleration is 50 G at most. Within 8 milliseconds, the speed of the water is dropping to zero. In this time, you cannot see any vacuum bubbles. That corresponds to an acceleration of 586 meters per square seconds, or 59.7 G. During the deceleration, there is a force of 29,300 Newton on a surface of 50 square centimeters. This is a pressure of 58.6 bar.
Excuse me.
The actual load on the disc is as high as if a heavy truck weighing 3 tons would rest on it.
So you can easily see how Waterhammer can potentially cause massive amounts of damage in your system, all by something that seems as trivial as closing a valve. And there's a check valve video that shows a check valve slamming open and closed, which shows some more cavitation. I'm gonna skip that for right now, and let's see. But I am going to show the video on how you can use a gas accumulator to mitigate pressure surge. That's one of the things that you can do by implementing surge suppression equipment. And let's see, that's this one here.
Fluids travel naturally at a given pressure and rate until a change in their flow happens. These changes occur when a pump starts or stops, or when a valve is opened or closed in a distant length of the piping, or if power is lost. The loss of power on a pump can create a column separation as the fluid in the pipe continues to flow. The fluid continues to flow through the piping until the column senses the stopped pump. Without the pump, the fluid flow now reverses direction and picks up speed until the vapor created by the column separation almost instantly collapses. The check valve closes after the vapor is dissipated due to the increased reverse flow pressure from the long length of piping. The fluid pressure created now builds in the long length of piping due to both the vapor collapse and the check valve closing. The pressure momentum of the fluid flow can result in a pipe rupture at a weakened point in the system, such as an elbow. The closing of the valve also can create pressure transients in the piping. As the water flows normally, a gate valve is shut a long distance away from the pump. The pump continues to run against the closed valve. The sudden closure of the valve, together with the momentum of the fluid column, can overstress the piping and can result in material failure as the pump continues to run.
Actually, it's the next one that talks about using the accumulator.
To prevent stress piping, the Young Engineering line of surge tanks has a gas-charged bladder installed in the tank. The tank's bladder is initially filled with the gas pre-charge. Fluid enters the tank through a screen and compresses the gas-filled bladder. This shock absorber effect protects the piping and its components. The initial startup of the pump supplies fluid to the destination, also filling 1/3 of the tank with fluid. When high pressures occur, such as a valve closing with the pump running, the piping pressure is dampened by further compressing the gas in the bladder. With the valve closed and the pump still running, fluid now reverses flow out of the tank from the pressure in the gas-filled bladder, pushing against the pump pressure. This action now oscillates, moving the equalized point in the piping back and forth until the fluid energy has returned to a static state.
So you can see how even just one event, such as a valve closure, can cause a lot of other things to interact with each other in very interesting ways. And as you have multiple branch pipes coming off of a main header, those pressure and velocity waves are going to travel down those flow paths as well. And then you're going to start having pressure and velocity waves that start interfering with each other throughout your entire piping system, and that's going to cause a lot of potential issues. And so there are several ways that you can mitigate Waterhammer. You can change the way that your components operate. So instead of slamming a valve shut really fast, you can close it more slowly. You can also close it over a different profile. You can change the way that the pumps turn on and off by operating those more slowly. You can implement the usage of gas accumulators or surge tanks or relief valves or vacuum breaker valves to help protect your system in different instances. And so I'm going to go ahead and open up not a Word document. I'm going to open up one of our standard impulse examples here to show you a valve closure here. This is a very simple system, just a single flow path, and the scenario is the flow is liquid ammonia. And so with liquid ammonia, it's got a really high vapor pressure of 146 psia. So you want to make sure that during the transient, the pressures stay well above that vapor pressure in order to help avoid cavitation. So how fast do you close the valve? Well, you can do different scenarios: a half-second closure, 1 second closure, or a 2 second closure. And for this particular scenario, it's a valve that's going to be closing from a CV value of 1,000 down to 0 in half a second. And then the same idea for the other two scenarios, but just 1 second and 2 second. So what I'm going to do here is I'm going to set up a quick batch run to run all these three scenarios. Right now we're only looking at 5 seconds for the analysis. I'm going to bring it out to 10. So as you can see, within 10 seconds, there's already 770 time steps in that simulation. And so Waterhammer is happening very, very fast. Your time scale is going to be on the order of 30 seconds to maybe a minute. You're not going to be looking at it much longer than that, because at that time you'll have something that you can do about that in order to help make things operate normally again. And so your time step is typically on the order of a few milliseconds. And I'm going to make sure remember how I said that impulse is going to break up the pipes into chunks in order to calculate what the transient pressures and flow rates are. I am setting this up so that it saves all the interior piping stations, because if I don't save those interior piping stations, I can't plot the pressure in the middle of a pipe, or I can't do an animation along the whole pipe using the output file, which is a lot easier. And so that's how I'm setting things up here. And then I'm going to do my batch run. I'm not going to do the base scenario. So now it's running each scenario sequentially. All right. Yeah, they're built into the software. We have, for impulse, about 20 different fluids that are built in. You can if you have access to the Chempac database, then there are over 700 different fluids that you can work with. Also, if you have your own fluid data information, you can easily create your own. So I'm going to load my half a second valve closure scenario. And as you can see here, the pressure values are very high for the maximum pressure. A lot of people will only look at what the maximum pressure is, and then they stop and they don't do any further analysis. And this doesn't complete the picture by any means. These pressure spikes may not even be real, because they can be that large after cavitation has happened for a really long time. So it's important to pay attention to when do these large pressure surges occur. It'll give you an idea of the time right here, and then you also want to see where they occur, what's going on during that time that causes the cavitation. And so for that, you're going to be doing graphs a lot more for analyzing your results. And so what I'm going to do here is I'm going to do a profile animation, and I'm going to look at the pressure and the vapor volume at the same time. Pressure, vapor volume, output file. Okay, so on the top graph, I have pressure. The bottom graph, I have vapor volume. So this will tell you when it starts to cavitate. The top graph, the dotted red line, is my maximum pressure profile. The dotted blue line is my minimum, and then the solid blue line is going to be changing as an animation over time. So with that, I'm going to turn off the legend to make it a little bit easier to see. And so my valve is right here at J3. And so, whoops, it for some reason put time in years rather than seconds. And what I'm going to do is I'm going to file this graph away for later. That way I don't have to reset the parameters each time. So when I go to play the animation, I'm going to slow it down. That valve is closing. Whoop, press the wrong button. That valve is closing, so you can see that it's approaching a significantly high pressure right at the valve there. Slow it down a little bit more. But it's not at the maximum value yet, so right now it's just hit the valve, and then it drops to vapor pressure, and you can see the cavitation that's happening. Once this vapor bubble that's forming collapses, you'll see a resulting pressure spike, and that causes additional pressure surges throughout your system. And so from this, you can see that there's a lot of chaotic behavior going on because of that cavitation. So now, what happens if I close the valve in 1 second rather than a half a second? I can reload that same graph here. And as you can see, the maximum pressures are not as high. The vapor volumes are not as large either. So closing the valve in a half a second, or in 1 second versus a half a second, it's going to do a better job of reducing the cavitation, but it does not completely eliminate it. And we want to make sure that the cavitation is completely gone. So finally, we'll take a look here at the 2 second scenario, where in 2 seconds, if we reload the same graph, you can see here on the bottom now, there's no more cavitation. So the cavitation is completely eliminated in that case. So now if you watch up here, you can see that the valve is closing, and then once it's fully closed, then you can see how it oscillates over time. Now, this is a linear valve closure. The way that you change a profile can also help reduce those surge pressures. And so your surge pressure is oscillating between these very extreme values, and you don't want that to happen in your system. We have a really neat capability where if you open up your valve, you can load in a standard valve characteristic, and that will change the profile in which it closes. And so if I go to edit my table, I'm going to create a CV versus open percentage curve. And let's say it's equal percentage. So I'll say fully open CV is 1,000. My percent increment is going to be 5%. I fill in the data. My transient duration is going to be, I'm going to close it in 2 seconds. My time increment will be 0.1, and it's going to close it. So here's my CV versus open percentage curve. Here's my new profile in which the valve is going to close over time. And so this is something that's more realistic than just a linear profile. So now when I go to rerun this scenario here, I can go to my graph results window, and as you can see here, the pressures are much, much smaller. And so that really does an excellent job of damping out those pressure surges. And maybe at this point in time, you are below your maximum allowable pressures and your pressure ratings. And so maybe this doesn't concern you. So you know that your answer is close the valve in 2 seconds over that profile. You don't need a relief valve or a surge tank or a gas accumulator or any other really expensive equipment. All you needed to do was change the way that you closed the valve at 2 seconds. Any questions on that?
I have a question. But, is there ways to model, like, you always have to put in, real numbers? Is it more trial and error, or can you, like, have it in variable?
Well, that's a good question, and so I had somebody call me up a few weeks ago, and they're saying that they wanted to use impulse to optimize a valve closure to mitigate surge. And it's like, what does that mean? And so, yes, it's going to be an iterative process, but as you can see here, it's actually really easy. Especially with the scenario manager, you can run the different cases together. You can also, instead of doing different scenarios, you could duplicate this system, and you can have the same system on the same workspace. But in this one, you would be able to change the valve closure in that guy, and that allows you to look at all the changes together, so you can animate each separate flow path there. And so for some things it's going to be trial and error. The key thing about Waterhammer analysis is there really is no boxed answer. It's a lot more of an art than it is just a science, and there's a lot of gray areas, especially when you're dealing with cavitation. And so
you can't set impulse to solve for the amount of time that you take to close the valve. If you give it you can't give it an input pressure that you want it to stay below.
we have had the thought of doing like a impulse GSC module, and that would certainly be something that would be able to do that. But that's probably a couple years down the road. So right now it would be iterative, but you can set up design alerts where rather than having to actually look at the results, you can just run a scenario, and if you have any constraints that have been violated, it'll alert you right away. That way, oh, this doesn't work, just move on to the next one. So there are several ways that you can help reduce surge in your piping systems. You can change the way that things change over time and slow them down. You can also change the initial steady state operating velocity by using larger diameter pipes. You remember that instantaneous Waterhammer equation, the pressure surge is directly proportional to the change in velocity. So if you have a lower velocity to start with, that's going to mitigate pressure surge in itself. You can also change the profile that the equipment operates, or you can install surge suppression equipment. Now, before we get into surge suppression equipment, there are this is just one of the codes that talks about for ASME B31.3 and B31.4 that talk about how you want to operate your systems so that they are safe. And so Impulse doesn't have those codes built into them, but again, you can set up a design alert which is per the code, and that'll let you know quickly if it's violated or not. Now, you can do a lot of sophisticated things just by simply closing valves in different ways. And so I've already showed you the linear closure on closing it over different periods of time. Half a second, 1 second, 2 seconds. Those will change what the resulting surge pressures are that you'll see. This particular situation here is where a valve is going to be closing from a CV of 1,000 down to 0 in 30 seconds. And if you look at the resulting pressure at the inlet and the outlet of the valve, you can see that hardly anything in the system actually changes until the very end. This is because of the relationship for CV. Okay? But at the very end, that's where you have a significant difference in pressure across the valve, and these pressure waves will propagate throughout the system. Let me open up that example really quick here. Okay, so here we have two systems on the same workspace. This valve is closing in 30 seconds linearly. There is a reference that talks about how you can use an 80-20 rule in order to help mitigate surge. So if you don't know how fast to close your valve or what profile, you could assume this. So what this means is, let's say that the valve takes 100 seconds to close over time. The 80-20 rule means that you're going to close the valve 80% of the way in the first 20% of the time that you're taking to close that valve. Then for the remaining 80% of the time, you're going to close it the rest of the 20% of the way. And that will have a significant bearing on reducing your pressure surges. And so for this valve down below, it's using the dual rate closure. So, 20% of the time, it's closed 80% of the way. And then the remaining 80% of the time, it's going to be the remaining 20% of the closure. So I'm going to run these two side by side here. Now what I have done is I have already created two groups of flow paths. This is a flow path and this is a flow path. And in the group manager, you can see that I have those two separate flow paths so we can analyze the results together at the same time. So here, if I have my linear closure and my dual rate closure, those are separate graphs, but you can also look at them at the same time, which is what I'm going to do here. So we'll start by just looking at the maximum and minimum values. So let me toggle a few of these things off here. Right now, I'm only looking at the maximum pressure for both systems. So you can see here that if I just turn on the top line, I can see that I have a much higher pressure than if I was doing a dual rate closure. So those maximum pressures are much less. Now if we look at just the minimum values, that's for the dual rate closure, and it's going to be minimized as well versus the linear closure. We can also plot what the pressures are at the valve itself. So if I select those two valves and then right click, I can do a pressure at the inlet and outlet of the valve. So this is really cluttered. Let me turn some things on and off. Okay, so let's look at the inlet of the valve for the linear closure. That's that. You can see after the valve is fully closed, it has some significant oscillations there. Versus the inlet of the valve for your dual rate closure, the pressure rise is going to be dampened out significantly, and then once it's fully closed, you're not going to have as large of oscillations on the upstream side of the valve. Let's take a look at the downstream side. Downstream for linear has really significant oscillations there versus how it's dampened out by using a dual rate. And so you can see how the 80-20 rule does a really good job of mitigating a lot of that surge in itself. Now there are other ways that you can do this in a creative fashion. Let's say that you have a situation where you have two valves in parallel because you've got some equipment that's left over. Well, what you might have is a really large valve right here and a small valve here. So this is how you can use multiple valves in parallel, where you actually stagger the closure times in order to help mitigate surge as well. And this will give you more of a dual rate effect. And so here we have a valve that's really large, so the CV is 25,000, but we're closing it in 22 seconds, so fairly quickly. versus a really small valve with only a CV of 3500, we're closing it over a 100-second time frame. And we're going to compare the results to each other. Okay. Those weren't supposed to be there, but all right. So I have 3 cases that I'm looking at. I've got my valves closing in parallel with staggered times. This system is just going to close it from a CV value of 25,000 down to 0 in 100 seconds. So this is the case that we're comparing. This case right here, the linear closure, is going to show the maximum pressures. And so this will help show that the dual rate and the staggered closure will be able to mitigate those surges. This valve here is basically the effective CV of this system. So they're going to match fairly closely to each other. One of the main differences is that this system up here includes losses from additional upstream and downstream pipes. This takes just a little bit longer. So here we have 2 individual profiles. We have our large, fast closing profile versus our small, long closing profile, and it results in the green line. So this is the bottom system on the green line that it's following there. Then ultimately what you're going to see here is that the linear closure is going to have this type of profile versus the dual rate or staggered is going to look more like this. It's almost done. One of the key things in impulse is you don't want to be ending up with like multi-hour long run times, and so that's all based upon how you break your pipes up into bits. So let's say that the longest pipe in your system is 10,000 feet long and the shortest pipe in your system is 1 foot long. It's just a simple connector pipe. Well, when you section your pipes, the pipes are going to be sectioned off of the shortest pipe in your system because you want to have a maximum time step that will give you good enough resolution to analyze the transient results. And so if you take that short 1 foot long pipe and you just put one section in there, that's going to break the long pipe up into 10,000 foot long sections. And that's going to make for a very long run time. The more sections, the more time steps, the longer your run times are going to be. There are a lot of methods that you can do in order to reduce that run time by either combining that short pipe into other pipes, neglecting it entirely, or perhaps by making its length arbitrarily a little bit longer. And even if you take into account those various approximations, it's still going to give you fairly accurate results. Okay, so here we've got our resulting profiles. I'm going to compare my maximum pressure profiles for those cases. So let's turn things on one at a time here. Okay, so my maximum pressure through my my linear closure path, that's the bottom system, it has a maximum pressure that's close to 75 psi. If I look at what my maximum pressure through the effective CV value is, that's this one here. This is the effective dual rate closure. You can see that the transient pressures are a lot lower in that case. Now, these additional 2 profiles are simply looking at the individual flow path through this valve and this valve. And so as you can see in those results, they are all very, very similar with each other. So this is just another example by how using that dual rate effective CV or your parallel valve closure and being creative with your existing equipment can help mitigate those surges and helps you avoid having to buy expensive equipment like a gas accumulator. Anybody have any questions on those valve closure scenarios? Okay, in Impulse, there are several different kinds of surge suppression equipment that you can model. You can model a gas accumulator, that's the one with the bladder that can go up and down. You can model a surge tank, where essentially the surge tank is open to the atmosphere. You can model a relief valve. You can model vacuum breaker valves. Vacuum breaker valves are designed where you want to maintain, you want to protect against low pressure situations. So if you're in a water distribution network, you typically want to keep your drinking water above atmospheric pressure. And so for a vacuum breaker valve, once your system pressure drops below atmospheric, your vacuum breaker valve will pop open to allow air in order to maintain atmospheric pressure in your pipeline. So let's look at some examples here. This is what a gas accumulator looks like, and you can model it in several different ways. I'm just going to go ahead and skip straight to the actual example here. Okay, so in this particular situation, we have a pump that is going to trip, and it's going to potentially have reverse flow, and if it has reverse flow, this transient model that I'm using for the pump trip is going to put a check valve on the pump for me. So if I have any reverse flow, I'm going to see in the messages that the internal pump check valve slams shut, and that's going to cause other pressure transients. For your gas accumulator, you can model it in two different ways. You can either assume it's pre-charged with an initial gas volume, or you can do a reference gas volume at a reference pressure. So either of those are different ways that you can model an accumulator. You would specify a polytropic constant of the gas inside the accumulator. You can model a flow restrictor. That way, when the liquid flows in and out of the accumulator, it's going to do so slowly, or more slowly than if there was no restrictor there. You can also, instead of modeling a physical short pipe in the workspace, which could potentially skew your run times, you can model the short connector pipe within the gas accumulator itself. Finally, you can enter maximum and minimum volumes, and that's going to be essentially the volume of your bladder. And so if your bladder is expanding all the way out, and the maximum volume here that you specify will limit it to that point. Now, what I'm going to show you here is two systems on the same workspace. I'm going to show you the results of using an accumulator versus not using an accumulator. So I'm going to duplicate this system here. And all I'm going to do in this accumulator is I'm going to go to the optional tab, and I'm going to ignore it. So it's going to act like a branch junction in that case. It's just going to sit there and do nothing. And I'm going to create a group with accumulator. And I'm going to create another group without accumulator. Make sure I'm saving my results. Oh, I got to section my pipes. Okay, got that done. Transient Control. So we're going to run this scenario for 30 seconds. And I'm saving all of my output the way that I want to. I keep telling the development team that they need to put like some elevator music into the solution progress window. That way it plays music while you're waiting for it to converge. Alright. So we don't have any warnings, which is good. But if you look at the event messages, this is telling you what's happening. And so here, it's telling you that both of my pumps trip at the very beginning of the simulation. That's the thing that's causing all the stuff to happen. Now, it says that my pump on the top has an internal check valve. It's closing fairly quickly. That's the system that has the accumulator that's being used. Versus this system here, it also has a check valve. It's going to close just a little bit later, and it doesn't have an accumulator to help dampen things out. So now let's take a look and see what's happening over time. Let's see. Plot multiple paths using groups. Output file. Let's take a look at the pressure. Awesome. Okay, so the blue line is with the accumulator, the red line is without the accumulator. And so it's right here where the accumulator is, right at this line. So when I play the animation, let me slow this down here. That pressure starts to drop really quickly when the pump trips. And so without the accumulator, that pressure is going to be dropping a lot faster than when you have the accumulator's fluid flowing back into the system to help protect things. Let me add one additional parameter. Let's take a look at flow. So that's the first thing. The second thing is for both of the systems, once the flow drops to 0, then you're going to see the pressure spike up here, and that's due to the check valve that's closing inside the pump. So we've got our initial pressure drop. You can see that the flow is dropping a lot faster with the accumulator. Then right when it gets to 0, so you can see how it takes a while to get down there because of the effect of the accumulator. And then now in the blue line, that's where the check valve inside the pump changed first. So now you can see where that little pressure oscillation here is going on. That's because your check valve closed. But it's resulting in a very small pressure surge. Now when the red line drops to 0, that's going to send a much, much larger pressure surge throughout the system when that check valve closes, and it's going to change significantly over time when it's reflecting off the boundaries of the system. And so here you can see how the effect of the gas accumulator in the blue line is basically really helping protect the system against those sudden pressure surges. I can also plot what the gas accumulator volume looks like over time. So if I right click on that and do a junction graph, here's my gas accumulator volume. So you can see that it grows, and so that's where it's allowing fluid into the system. So your gas bladder is expanding, and then it starts contracting, and then it oscillates and it dampens out over time. So if we ran this out for about a minute, you would see that essentially you're at a new steady state at that point, and the system is dampened out effectively. So that's modeling a gas accumulator with impulse. Any questions on that part of it? Now let's talk about surge tanks. Surge tanks are similar to gas accumulators. However, you're going to typically have a open to atmosphere situation. Now, a surge tank you're going to want to put it in a lower elevation area, because if you're trying to use a surge tank to protect the system and you have it at a high point, and it could potentially require a really high liquid level inside the tank. And so that's where you want to have it at lower points. So let me open up my surge tank model here. So the surge tank junction is really cool. If you were to open it up, it's got a picture of what it looks like. And so initially, I don't know what my initial liquid height is. I don't know what that level is. So by the initial steady state simulation, that value is going to be calculated. When you look at the results for how the liquid level inside the surge tank changes over time, you're going to see that the initial liquid height is probably around 3 or 4 feet high. You've got your cross-sectional area. You can do either constant or variable. You can do flow restrictors or short connector pipes like you can with gas accumulators. There's also an optional thing that you can do where you can model it as a dipping tube right here. And so the dipping tube will put a tube down the tank right here, and once the liquid height gets to the bottom of the tube, then it's going to act like a accumulator at that point, and it's got a little bit of extra cushion inside your surge tank there. So we're doing another situation where we've got a sudden valve closure, and this is not so sudden. It's closing in 5 seconds, and it's using the 80-20 rule. You can show the graph. That's the profile that the valve is closing. And we're going to take a look and see how the surge tank can mitigate those pressure surges. The problem statement says you want to make sure that your surge pressure does not exceed 50 psia. And my pumps are going to operate continuously over time, because during our simulation time period of 30 seconds, the pumps are just going to keep operating until something tells them to shut off. So I'm going to go ahead and run my two scenarios together side by side. Again, we've got the elevator music going. Okay. Now, what this is telling you is that one of the pumps has reverse flow and the data may be unreliable. So what that means is, for this pump here where that's happening, once your flow drops down to below 0 and you have reverse flow, what's the pump head that you should use? We don't know. So we just use the shutoff head at that point, and that's not going to be accurate. And so the next thing that you would want to do is implement a better prediction of the pump head for when you have reverse flow or if the pump starts spinning backwards. And for that, you would use a 4-quadrant model. And so we have 21 different data sets that are based off of different specific speeds for pump characteristics. And those 4-quadrant data sets will allow you to have a more accurate pump head prediction if it's flowing backwards or spinning backwards. But we're not going to do that right now. Let's take a look at some graphs here. Okay, so here's our maximum and minimum pressure profile. Let's take a look at the maximums first. I'll put my legend in the middle. So, the red line down below, that is your maximum pressure profile when using a surge tank. So you can see here that it's much, much lower than these really large pressure spikes way above. Now, why are these pressures so funky? Well, cavitation is happening. How can we check that we've got cavitation? Well, if we now look at the minimum pressures, you can see by the green line that the pressures are at vapor pressure. And so that's what's causing the cavitation. Now again, the maximum profiles only give you so much information. You want to see what's happening over time. So for that, I'm going to do another graph where I'm doing my two flow paths, and I'm going to look at the animations. I'm going to make my scale a little bit different here. I'm going to shorten that down to 3200. Okay. And so the blue line is with the surge tank, red line is without the surge tank. I'm going to take my legends off here. And so as the valve closes, the pressures increase for both of them. But you can see here that the red line without the surge tank, those pressures are going up a lot higher, a lot faster. Here's where your surge tank is. It's basically going to act as a really good dampener between the upstream and downstream portions of that surge tank. So you can see how things are reflecting off the surge tank right here, and it's not causing any sudden pressure surges upstream. Versus this situation up here is now completely off the charts. When this pressure up above drops down and it reflects, it's going to hit vapor pressure, and that starts causing the cavitation spikes, and things start going crazy with that. And so you can see how the surge tank even protects the downstream side a lot better as well. So the next thing that you want to do is you want to make sure your surge tank isn't overflowing. And so my surge tank here only was 10 feet high. So in this 30-second simulation, how high does that liquid get? Well, you can graph that by right-clicking. Look at the surge tank liquid height. And in just 30 seconds, the liquid height's not going up very high. And so the surge tank there will do an effective job of being able to mitigate that surge. One thing about surge tanks and accumulators is you want to make sure that you size them correctly and that you locate them correctly, because their size and location is going to change the way that your overall system responds. So if you don't size them properly, or if you put them in the wrong place, then it could actually make your system worse. So what you would do, it's an iterative process, and so you can use the split pipe feature. That's where you hover over a junction, hold the shift key, and then click and drag it on top of a pipe. That will split the pipe in half. And so you can just put a whole bunch of surge tanks onto your workspace here, and as you're trying to figure out where the best spot is for your surge tank, just turn all the rest of them off and use the special condition to ignore them. And so if you just click on ignore surge tank, then it'll act like a branch junction. That's an effective way to be able to figure out where to put your surge suppression equipment. Any questions on that? All right, so I think that I'm unfortunately out of time here. The last two things that I was going to talk about is relief valves and vacuum breaker valves. And so if you grab the flash drive on your way in, if you didn't, make sure you grab one on your way out. Here's what the contents are on those flash drives. If you open them up, there is the full workshop presentation, so you've got that electronically. Also, there's a timed software evaluation. So we have the latest release of Fathom, Arrow, and Impulse on your flash drives with a temporary license that will let you use the full version until May 6th. And so these instructions will show you how to install them on your computer. If you don't have access to being able to install the software on your computer at work, install them on your computer at home. That's perfectly fine. And so you install the software, use the license numbers for that's in this text file, and then you'll put this file where it says to go from the instructions, and that'll allow you to play with the software. If you want to go over with me what I was going to talk about with relief valves and vacuum breaker valves, I'll give you my business card. Give me a call later this week or next week, and I'll be happy to give you a further web demonstration on those two other types of situations. So, on that note, do any of you guys have any questions for me on anything? Everybody have a better idea of what the heck Waterhammer is?
Ooh, I got a question.
Yeah.
What can you run in Fathom through the Transient?
So Fathom does have a extended time simulation add-on module that allows you to model transients. Those transients are what we call slow transients. So that's where you have something that's changing over a much longer period of time. It's changing so slowly that it's basically assuming that you don't have any significant Waterhammer effects of it's not capturing the pressure and velocity waves that are passing throughout the system. So it's assuming that every time step that it solves is basically at a steady state, and it doesn't have waves going back and forth. You're going to have much longer time scales that you're looking at, several minutes, hours, days. It gives you a good feel for how long it takes your tanks to fill up and drain over time. You can see how the system interacts dynamically with itself. The modules are included with your evaluation license. And so when you go to open up any of our software products, go to Help menu, and then Show Examples, and then pick your desired units. That pulls up our examples help file. It has all of our walkthrough tutorials right here, and then it also has a modules section. And the modules section contains module-specific examples that you can work through or read through, and that'll give you an idea of how those modules are able to be used. If anybody has any questions, we're also doing a Q&A session from 4 to 5 this afternoon. If you happen to bring your computers and you want to have me help install the evaluation on them for you, I'll be happy to do that. You can play with the software. You can ask any questions about the software that you had. And then other than that, just feel free to give me a call later on, and I'll be happy to answer any other questions that you have on surge suppression. So thank you very much, and we'll take a quick break. Scott, do you know when the next session begins?
Maybe
2:45?
yeah.
Okay. All right, so am I staying over here or am I moving? Okay, so on Trey's side, he's going to be talking about conflict resolution with pump system interaction.